ZigBee is an IEEE 802.15.4-BASED specification for a suite of high-level communication protocols used to create personal area networks with small, low-power digital radios. The technology defined by the ZigBee specification is intended to be simpler and less expensive than other wireless personal area networks, such as Bluetooth or Wi-Fi. Applications include wireless light switches, electrical meters within home displays, traffic management systems, and other consumer and industrial equipment that requires short-range, low-rate wireless data transfer. Its low power consumption limits transmission distances to 10 to 100 meters line of sight, depending on power output and environmental characteristics. ZigBee devices can transmit data over long distances by passing data through a mesh network of intermediate devices to reach more distant ones. ZigBee is typically used in low data rate applications that require long battery life and secure networking. ZigBee has a defined rate of 250 kbit per second, best suited for intermittent data transmissions from a sensor or input device. ZigBee was conceived in 1998, standardized in 2003, and revised in 2006. The name refers to the waggle dance of honeybees after their return to the beehive. Overview: ZigBee is a low-cost, low-power, wireless mesh network standard targeted at wide development of long battery life devices in wireless control and monitoring applications. ZigBee devices have low latency, which further reduces average current. ZigBee chips are typically integrated with radios and with microcontrollers that have between 60 to 256 kilobytes flash memory. ZigBee operates in the industrial, scientific and medical radio bands. 2.4 GHz in most jurisdictions worldwide, 784 MHz in China, 868 MHz in Europe and 915 MHz in the USA and Australia. Data rates vary from 20 kbit per second to 250 kbit per second. The ZigBee network layer natively supports both star and tree networks, and generic mesh networking. Every network must have one coordinator device, tasked with its creation, the control of its parameters and basic maintenance. Within star networks, the coordinator must be the central node. Both trees and meshes allow the use of ZigBee routers to extend communication at the network level. ZigBee builds on the physical layer and media access control defined in IEEE standard 802.15.4 for low-rate WPANs. The specification includes 4 additional key components: network layer, application layer, ZigBee device objects and manufacturer-defined application objects which allow for customization and favor total integration. ZDOs are responsible for a number of tasks, including keeping track of device roles, managing requests to join a network, as well as device discovery and security. ZigBee is one of the global standards of communication protocol formulated by the relevant task force under the IEEE 802.15 working group. The fourth in the series, WPAN low rate, ZigBee is the newest and provides specifications for devices that have low data rates, consume very low power and are thus characterized by long battery life. Other standards like Bluetooth and URD address high data rate applications such as voice, video, and LAN communications. History: ZigBee-style self-organizing ad hoc digital radio networks were conceived in the 1990s. The IEEE 802.15.4-2003 ZigBee specification was ratified on December 14, 2004. The ZigBee Alliance announced availability of Specification 1.0 on June 13, 2005, known as the ZigBee 2004 specification. Cluster library in September 2006, the ZigBee 2006 specification was announced, obsoleting the 2004 stack. The library is a set of standardized commands, organized under groups known as clusters with names such as Smart Energy, Home Automation, ZigBee Lightlink, ZigBee Pro, also known as ZigBee 2007. The enhanced ZigBee Pro specification was posted on the 31st of October 2007, and was finalized that same year. ZigBee Pro is fully backward compatible with ZigBee 2006 devices. A ZigBee 2007 device may join and operate on a ZigBee 2006 network and vice versa. Due to differences in routing options, ZigBee Pro devices must become non-routing ZigBee N devices on a ZigBee 2006 network, and ZigBee 2006 devices must become Zs on a ZigBee Pro network. The applications running on those devices work the same, regardless of the stack profile beneath them. The first ZigBee application profile, Home Automation, was announced November 2, 2007. Use cases: ZigBee protocols are intended for embedded applications requiring low power consumption and tolerating low data rates. The resulting network will use very small amounts of power. Individual devices must have a battery life of at least 2 years to pass ZigBee certification. Typical application areas include home entertainment and control, home automation such as IQ-IVICON, smart lighting, advanced temperature control, safety and security, movies and music, wireless sensor networks, starting with individual sensors like Teleb, T-Mote and Iris from MEMSIC, industrial control, embedded sensing, medical data collection, smoke and intruder warning, building automation, standard and profiles. The ZigBee Alliance is a group of companies that maintain and publish the ZigBee standard. The term ZigBee is a registered trademark of this group, not a single technical standard. The Alliance publishes application profiles that allow multiple OEM vendors to create interoperable products. The relationship between IEEE 802.15.4 and ZigBee is similar to that between IEEE 802.11 and the Wi-Fi Alliance. License for non-commercial purposes. The ZigBee specification is available free to the general public. An entry-level membership in the ZigBee Alliance, called Adopter, provides access to the as-yet unpublished specifications and permission to create products for market using the specifications. The requirements for membership in the ZigBee Alliance cause problems for free software developers because the annual fee conflicts with the new general public license. The requirement for the developer to join the ZigBee Alliance similarly conflicts with most other free software licenses. The ZigBee Alliance board has been asked to make their license compatible with GPL, but refused. The refusal came, even though Bluetooth had already changed their license to make it compatible with GPL. Application profiles. The current list of application profiles either published or in development are released specifications: ZigBee Home Automation 1.2, Smart Energies 1.1b, Telecommunication Services 1.0, Healthcare 1.0, RF4CE, Remote Control 1.0, RF4CE, Input Device 1.0, Remote Control 2.0, Lightlink 1.0, IP 1.0, Building Automation 1.0, Gateway 1.0, Green Power 1.0, Retail Services. Specifications under development: ZigBee Smart Energy 2.0, Smart Energy 1.2, 1.3, Lightlink 1.1, Home Automation 1.3. The ZigBee Smart Energy v2.0 specifications define an IP-based protocol to monitor, control, inform and automate the delivery and use of energy and water. It is an enhancement of the ZigBee Smart Energy version 1 specifications, adding services for plug-in electric vehicle charging, installation, configuration and firmware download, prepay services, user information and messaging, load control, demand response and common information and application profile interfaces for wired and wireless networks. It is being developed by partners including HomeGrid Forum, responsible for marketing and certifying ITUTG.HN technology and products, HomePlug Powerline Alliance, International Society of Automotive Engineers SAE International, IPSO Alliance, SunSpec Alliance, Wi-Fi Alliance. In 2009, the RF4CE Consortium and ZigBee Alliance agreed to jointly deliver a standard for radio frequency remote controls. ZigBee RF4CE is designed for a wide range of consumer electronics products, such as TVs and set-top boxes. It promises many advantages over existing remote control solutions, including richer communication and increased reliability, enhanced features and flexibility, interoperability, and no line-of-sight barrier. The ZigBee RF4CE specification lifts off some networking weight and does not support all the mesh features, which is traded for smaller memory configurations for lower-cost devices, such as remote control of consumer electronics. With the introduction of the second ZigBee RF4CE application profile in 2012 and increased momentum in MSO market, the ZigBee RF4CE team provides an overview on current status of the standard, applications, and future of the technology. Radio hardware. The radio design used by ZigBee has been carefully optimized for low cost in large-scale production. It has few analog stages and uses digital circuits wherever possible. Though the radios themselves are inexpensive, the ZigBee qualification process involves a full validation of the requirements of the physical layer. All radios derived from the same validated semiconductor mask set would enjoy the same RF characteristics. An uncertified physical layer that malfunctions could cripple the battery lifespan of other devices on a ZigBee network. ZigBee radios have very tight constraints on power and bandwidth. Thus, radios are tested with guidance given by Clause 6 of the 802.15.4-2006 standard. Most vendors plan to integrate the radio and microcontroller onto a single chip, getting smaller devices. This standard specifies operation in the unlicensed 2.4 GHz, 915 MHz and 868 MHz ISM bands. 16 channels are allocated in the 2.4 GHz band, with each channel spaced 5 MHz apart, though using only 2 MHz of bandwidth. The radios use direct sequence spread spectrum coding, which is managed by the digital stream into the modulator. Binary phase shift keying is used in the 868 and 915 MHz bands, and offset quadrature phase shift keying that transmits 2 bits per symbol is used in the 2.4 GHz band. The raw, over-the-air data rate is 250 kbit per second per channel in the 2.4 GHz band, 40 kbit per second per channel in the 915 MHz band, and 20 kbit per second in the 868 MHz band. The actual data throughput will be less than the maximum specified bit rate due to the packet overhead and processing delays. For indoor applications at 2.4 GHz, transmission distance may be 10 to 20 meters, depending on the construction materials, the number of walls to be penetrated and the output power permitted in that geographical location. Outdoors with line of sight, range may be up to 1,500 meters depending on power output and environmental characteristics. The output power of the radios is generally 0 to 20 dBm. Example commercial SoCs. Device types and operating modes. ZigBee devices are of 3 types. ZigBee Coordinator. The most capable device. The coordinator forms the root of the network tree and might bridge to other networks. There is exactly one ZigBee coordinator in each network since it is the device that started the network originally. It stores information about the network, including acting as the trust center and repository for security keys. ZigBee router. As well as running an application function, a router can act as an intermediate router, passing on data from other devices. ZigBee end device contains just enough functionality to talk to the parent node. It cannot relay data from other devices. This relationship allows the node to be asleep a significant amount of the time, thereby giving long battery life, as ED requires the least amount of memory, and therefore can be less expensive to manufacture than a ZR or ZC. The current ZigBee protocols support beacon and non-beacon enabled networks. In non-beacon-enabled networks, an unslotted CSMA/CA channel access mechanism is used. In this type of network, ZigBee routers typically have their receivers continuously active, requiring a more robust power supply. However, this allows for heterogeneous networks in which some devices receive continuously, while others only transmit when an external stimulus is detected. The typical example of a heterogeneous network is a wireless light switch. The ZigBee node at the lamp may receive constantly, since it is connected to the mains supply, while a battery-powered light switch would remain asleep until the switch is thrown. The switch then wakes up, sends a command to the lamp, receives an acknowledgement, and returns to sleep. In such a network, the lamp node will be at least a ZigBee router, if not the ZigBee coordinator. The switch node is typically a ZigBee end device. In beacon-enabled networks, the special network nodes called ZigBee routers transmit periodic beacons to confirm their presence to other network nodes. Nodes may sleep between beacons, thus lowering their duty cycle and extending their battery life. Beacon intervals depend on data rate. They may range from 15.36 milliseconds to 251.65824 seconds at 250 kbit per second. From 24 milliseconds to 393.216 seconds at 40 kbit per second, and from 48 milliseconds to 786.432 seconds at 20 kbit per second. However, low duty cycle operation with long beacon intervals requires precise timing, which can conflict with the need for low product cost. In general, the ZigBee protocols minimize the time the radio is on, so as to reduce power use. In beaconing networks, nodes only need to be active while a beacon is being transmitted. In non-beacon-enabled networks, power consumption is decidedly asymmetrical. Some devices are always active, while others spend most of their time sleeping. Except for the Smart Energy Profile 2.0, ZigBee devices are required to conform to the IEEE 802.15.4-2003 low-rate wireless personal area network standard. The standard specifies the lower protocol layers, the physical layer, and the media access control portion of the data link layer. The basic channel access mode is carrier sense, multiple access, collision avoidance. That is, the nodes talk in the same way that humans converse. They briefly check to see that no one is talking before they start, with three notable exceptions. Beacons are sent on a fixed timing schedule and do not use CSMA. Message acknowledgements also do not use CSMA. Finally, devices in beacon-enabled networks that have low latency real-time requirements may also use guaranteed time slots, which by definition do not use CSMA.